So problem 2.10 goes like this. A rod of 10 mm diameter and 80 mm length with thermal conductivity 16 watt per meter Kelvin protrudes from a surface at 160 degrees Celsius. The rod is exposed to air at 30 degrees Celsius with a convection coefficient of 25 watt per meter square degree Celsius. How does the heat flow from this rod get affected if the same material volume is used for two fins of the same length? Assume short fin with end insulated. So let us draw the schematic of this problem first. Now once again in this problem, there are two cases. In first case, there is a rod and it is attached to the base surface. Actually, the orientation is getting changed. This rod is there. And this rod is attached to this base surface. Okay, let us say at surface temperature Ts. Its diameter is initially its capital D and length is capital L. Let's say thermal conductivity of this rod material is K. It is exposed to the surrounding at temperature T infinity and convective heat transfer coefficient H. So this is case number 1. Now in second case, what we are doing, this rod is divided into two number of fins. Instead of one, now we have divided into two number of fins, keeping the volume same. Okay. So obviously their diameter will be decreasing now. Volume will remain same. The hatching line signifies the cross-sectional area. How does it look like actually? Now same base surface is there, but instead of single fin, now we have divided it into two fins of, let's say, diameter D, a small d. Their thermal conductivity is same as that of previous fin. They are attached to the same base surface at temperature Ts and they are exposed to the same environment. And their length is also same as of previous fin, previous single fin. Got my point? Got the schematic? This is case number 2. So instead of larger diameter fin. In second case, I have divided into two small fins, each having diameter small d and length L. So figure will be fins attached to base surface. Now here I request you, make it practice to always give some title to your figure, not only in heat transfer, in any course. Whether whenever you draw a figure, always mention its title. It is always a good practice. Fin attached to the base surface. Depending upon your understanding, you can give title. After the schematic, let us list all the given things. So for case 1, diameter is 10 mm, length is 80 mm, thermal conductivity is 16, and base surface is 160. So capital D is 10 mm, that is 0.01 meter. Length is 80 meter, 0.08 meter. Thermal conductivity of the material of the rod 16. Watt per meter degree Celsius. Base surface temperature is 160 degrees Celsius. Surrounding temperature is 30 degrees Celsius. H value is 25. So all these values I could sum up. And small diameter I don't know. And number of fins in second case 2. Okay. Once again, let us write down all those assumptions. So assumptions you are supposed to repeat every time. The set of assumptions for all problems in case of fins are almost same. Okay, so let me write it for you. One-dimensional steady state heat transfer generally what happens in case of heat transfer, set of assumptions are almost same for all the problems for a particular unit. Depending upon the nature of problem, one or two assumptions may get changed. Otherwise, they are almost same for particular unit. No heat generation within the fin itself. That is Qg is equal to 0. Assumption number 3, no thermal contact resistance between base and fin root surface. As a consequence of this, base surface temperature will be fin root temperature. Assumption number 4, isotropic and homogeneous fin material. I am writing each and every assumptions again and again for you. That is K is equal to constant. Assumption number 5. Uniform properties of fluid. And last but not least, and very important, you are supposed to solve this problem considering insulated tip fin. Now, mostly problems in case of fins are solved considering insulated tip fin boundary condition only. Otherwise, you can take any formula are given to you, but why it is recommended, calculations become easier. Okay. So, what you are supposed to find out once again, we are supposed to find out once again Q1 and Q2. That is rate of heat transfer from this fins, from this single fin of larger diameter, and rate of heat transfer from the two fins of smaller diameter. Okay. Now let us solve one by one. So once again, we are interested to calculate heat transfer rate by insulated tip fin. So once again, from data book, for insulated tip fin, the rate of heat transfer, always write down this from HT data book. In my case, it is page number 50. Okay, HT data book by Othander Raman. And what is that formula? HPKAC and number of fins. If number of fins are n, then it becomes n into square root of HPKAC Ts minus T infinity 10 of hyperbolic ml. Got it? So let us calculate for case 1. Number of fins in case 1 is 1 and diameter is 0.01 meter and length is 0.08 meter. This is case 1. Let me check. Yes. N1 is equal to 1. Number of fins. Please write. Do not get confused. 0.01 is the diameter, length is 0.08 meter and number of fins 1. Okay. So how can I calculate heat transfer rate in case 1? N1 into square root of H E1 A AC1, because diameter is changing, so perimeter and cross sectional area will also get changed in case 1 and 2. That is why I am representing by suffix 1 in case of 1. Base and surrounding temperatures are same, 10 of hyperbolic M1L. Okay. So let us calculate for pin 1. Perimeter will be what? Pi into D, because it is a pin fill. So pi into 0.01. Tell me what will be this value. I could get this value. I don't have the value. Please tell me this value. Otherwise, I have to calculate the 0.14 or pi into 0.01. It comes out 0.03141 meter. Similarly, cross-sectional area AC1 will be pi by 4 d square. Pi by 4 into 0.01 square. What will be this value? Pi by 4 into 0.01 square. Please check whether I have calculated correctly or not. 7.85 into 10 to power minus 5 meter square. So I have the P1 value, cross-sectional value for pin of larger diameter in case 1. And what will be P1? HP1 K into AC1. Thermal conductivity is not going to change. The value of H is 25 and K is 16. The value of K is 16 and cross-sectional area is 7.85 into 10 to power minus 5. Can someone tell me what will the value of M1? Does it come 25? Please check this value. I am waiting for your response. Is it correct? So if it is correct, now I can calculate heat transfer rate from for case 1. N1 is 1 into H is 25, perimeter is 0.01, sorry, not 0.01, 0.0 P141. This is the value of perimeter P1. HP after PK value is 16 and cross-sectional value is 7.85 into 10 to power minus 5. This is under root HPKC. What is the value of TS and T infinity? 160 and 30. Ten of hyperbolic. The value of M1 is 25 and the value of L is 0.08. So the value of heat transfer rate in case 1 comes out, if I am correct, 3.935 watt. Simply formula based. Please someone check. $4.082, it is what? Saurabh Mate, it is what? Saurabh, 4.082. Final value of heat transfer rate. Okay, no issue. 3.935 will also work. Okay. Now case 2. In case 2, there are two number of fins of some diameter small d that I don't know, and length remains same. So calculation will also go in the same fashion. Okay. So if I want to calculate Q2, it will be N2 into square root of H P2, because diameter is changing, so parameter will change, K into AC2 Ts minus T infinity 10 of hyperbolic. M2 will also get changed in second case. But here the big problem is how to calculate this diameter D. So this is the beauty of this problem. Now can someone suggest how can I calculate small diameter D? Unless I could calculate D, I cannot calculate parameter, cross-sectional area and M2 value. So I cannot calculate Q2. So for that, you need to go to problem statement once again. What it is saying, the problem is saying, how does the heat flow from this rod get affected if the same material volume is used for two fins of the same length? What does mean? The volume of the larger fin is equal to volume of two number of fins. So this we will be using. Volume of fins, let me write it correctly. Volume of large fin, large single fin actually, is equal to volume of two small fins. Got my point? That is, cross-sectional area of first fin will be equal to twice into cross-sectional area of single fin. Got it? Or this will be AC1. I know the value of AC1. AC1 is equal to twice into pi by 4 into small d square, because diameter of the small fin in case 2 is small d. AC1 value, I have this AC1 value, that is cross sectional area of larger fin 7.85 into 10 to power minus 5 meter square twice into 5 by 4 into d square. From here, calculate the value of small d. Oh, this is cross-sectional area. I need to calculate volume. So you are supposed to multiply L as well, isn't it? Volume of large fin is equal to twice of volume of small fins. And volume is nothing but area into length. So that is there. So L will get cancelled because we are taking both the fins of same length. From here, the diameter value will be 0.00707 meter. So let me explain this step once again. In order to find out the value of diameter of small fins, we have used the condition given in the problem, that is volume of single large fin is equal to volume of two small fins. So from this, I could calculate diameter of the small fin as 0.00707 meter. Now I can calculate perimeter of the single fin, that is pi d, pi into 0.0070. Tell me what will be the value. Cross-sectional area of single fin, pi by 4 d square, that is pi by 4 into 0.0070 square. Tell me what are these values. So let me calculate for you. So the perimeter comes out 0.0222 meter and cross-sectional area comes out 3.925 into 10 to power minus 5 meter square. And finally, the value of M2 HP2 over KAC2. Those who want to leave, they can post their roll number and can leave the session. After posting their roll number, they can leave. Because this problem will go for another 5 minutes. So H value is 25, P2 is 0.0222, K value is 16, and cross-sectional area is 3.925 into 10 to power minus 5. So from here, the value of M2 will be, please calculate it. Will I get 29.73 meter inverse? Let us calculate this.
Yes, sir. 29.728.
Correct? Okay. 29.73. Correct value. So now you can calculate Q2. Now only mathematics remains. Twice into square root of HP is 20, H is 25, P2 is 0.0222, K is 16, the cross sectional area of smaller fin is 3.925 into 10 to power minus 5. TS is how much? 160, 160 and 30, and finally 10 of hyperbolic 29.73 into 0.08. So please calculate this value.
So 29.73 into 0. It's not
What is the
visible.
value?
The calculation.
What is the value you are getting?
Sir, the screen is not visible fully.
Just a minute, just a minute. Is it visible now?
No, sir, it's gone blank.
But I am presenting. I did not stop presenting.
Now it's visible.
Okay. So I could get this value. Q2 something is coming around as 4.770 watt.
Yes, sir, 4.771.
Okay. Almost correct. Okay. So what was the value of Q1? If you will 3.935 watt and Q2 is 4.770 watt, isn't it? So can I calculate the percentage increase in order to compare? That is Q2 minus Q1 over Q1 into 100. 4.770 minus 3.935 divided by 3.935. So this will be around how much?
0.2121.
That is 21.2%, isn't it?
Yes,
Like,
21%.
yes. So now once again we can draw very important conclusion. Uh, we have defined one parameter. See, numerical is okay, but it is giving you One important conclusion. See, in case one, we have used a larger diameter fin of some length. In the case two, we have divided that fin into two fins of smaller diameter. So keeping the length same, keeping the volume same, instead of single fin, I am using now two fins. So that causes increase in heat transfer. So if you remember one term, effectiveness of fin. And that effectiveness of fin is nothing but is directly proportional to parameter and inversely proportional to cross-sectional area. So what it happens actually when you reduce the cross-sectional area and keeping perimeter constant, effectiveness increases. So same thing is happening here itself. Instead of single fin of larger diameter, if you are reducing its cross-sectional area, it will causing heat transfer rate. That is, fins will be more effective if instead of single larger diameter fin, they are used of a smaller diameter, but their number is increased. Okay, so that is the conclusion. Thin fins of more numbers will be more effective in enhancing heat transfer rate rather than large fin of single number. That is very important conclusion, isn't it?